Hello, everyone, and thank you for joining us today. The topic of the presentation today is unifying machine learning and quantum chemistry with a deep neural network. I'm a machine learning developer at ExxonMobil and stream owner of machine learning in chemistry and chemical process at ACE. And as you know, ACE is a community of machine learning practitioners and researchers that are gathered around different topics in AI research, engineering, and products. We host free live sessions like this 3 to 5 times a week. And if you want to see more like this, you can just subscribe on our YouTube channel, which is ML Paper Explained. And also you can visit our website, AI.SCIENCE. We currently have more than 14 different streams that are focused on various ML topics. And this session is ML in chemistry and chemical process. Hope you enjoyed it. Hope you enjoyed the presentation and come back. So today, our presenter is Dr. Reinhard. He is an assistant professor of computational chemistry and UKRI Future Leaders Fellow at University of Warwick in UK. And he has previously worked as a postdoctoral researcher at Yale University after completing his PhD. Thank you, Reinhard, for joining us and for accepting to give us talk about your latest publication in Nature Communication. And yeah, floor is yours, and please.
All right, thanks, Mehrshad. Thanks for having me. So I should start with a few disclaimers. I'm not a machine learning expert. I'm a chemist, very much so, and so I will do my best to convey the technical aspects, but naturally my focus is very much on the chemistry. I should also say, and I'm going to do the acknowledgement first here, that this is very much an interdisciplinary effort, which is one of the reasons why working in machine learning and chemistry and in computational chemistry is so exciting at the moment, because you get to talk to a lot of people from different fields. And so the colleagues that are involved in this are the machine learning experts in the group of Klaus Robert Müller at the TU Berlin. And so the model that we use is very much the brainchild of Christoph Schütt here. And his colleague Michael, who manages to not have a single picture of himself on the internet, is also very much involved. And our colleagues here in Warwick and in Luxembourg. The one thing I want to point out on this slide, which I think is really useful for the young folks, is this logo here, the IPAM logo. And the IPAM is the Institute of Pure and Applied Mathematics at UCLA. And it's a fantastic place. It's basically the place where this collaboration team here met. And so they're hosting long programs, which are very well funded, and which allow people to come together to work on problems in how machine learning mathematics applies to different things. So please look it up. It's a fantastic place. Very much the reason how we got to create this. So my group, my research focus is on using quantum mechanics-based simulations to look at chemical reactions. And so we're interested in problems in catalysis, problems in surface chemistry, and in nanotechnology. And the focus is very much to use quantum mechanics to entangle the complicated motion of electrons and atoms and how they interact with light. And so it's very hard to talk about the machine learning aspects of this without talking about quantum mechanics itself. And if you're not an expert, if you're not a physicist yourself, if you don't know anything about quantum mechanics, it's also very hard to give a very, very brief intro into it. So I feel sometimes when it's hard to talk about things, it's better to sing. And obviously I'm not going to do that. But I have somebody here who is going to give us a very brief song introduction to quantum mechanics. Mehrshad, please feel free to
left on a twin, one up, one down in the ground state. With S&P and quadruple degeneracy, the second shell can be filled up with 8. The higher angular power spread all the beautiful flowers and middle families that come into play. Well, here's a carbon with 6C. This ain't nothing tricksy, but we're gonna make some methane today. With hydrogen, it's like, oh, atoms, I feel your tug. Got my electrons bugged out, pulling on me. Come on now, settle around me. I'll hybridize to sp3, say, oh, carbon, here's our touch. Spread out 109.47 degrees. Come on now, follow our lead. Come on now, follow our lead. Molecules take the shape they do, combining states of the quantum aromatically bonding. High, low, high, low, high, low, high. Aromatically bonding. Look at benzene in a ring, they hold their truth. When orbitals take the shape they do. Come bond with me, baby, come bond. 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 Polymers take the shape they do. Combining base level residues like RNAs, ACGU. With their hydrogen bonding, peptides make a chain and group. And get up lead sheets and corkscrews. With the secondary links they fold and move. They're all over your body. Come bond with me, baby, come bond. Come bond with me. They're all over your body. Come bond with me, baby, come bond. Come bond with me. They're all over your body. Come bond with me, baby, come bond. Come bond with me. They're all over your body. You're a chemical machine, it's best you do. The molecules take the shape of you.
What you should have seen in this video, very briefly, is this equation here, or a part of it. And so this is the time-dependent Schrödinger equation, which is pretty much the essence of quantum mechanics and chemistry. And it connects the kinetic energy and the interactions between atoms and electrons, and gives rise to the molecular wave function. So what you see here is a picture of an Austrian banknote showing Schrödinger himself, and also the symbol psi for the wave function. And so what we have here is the so-called Hamiltonian, which pretty much gives rise to all of the chemical and electronic properties of molecules that we're interested in. And we can rewrite this into a much simpler form called the time-independent Schrödinger equation. So basically, quantum mechanics we can view as this equation toolbox which allows us to predict any molecular properties. And it connects the atomic positions and the atomic composition. And in fact, so that this involves electronic energies, molecular dipoles, forces that act on the atoms, and all sorts of other properties. And so once we have the wave function, we can pretty much predict any other property, right? So this is a key message here. And so the problem, though, is that we cannot solve this exactly for anything with more than 2 electrons, anything with more than 2 particles. The machine learning is quite helpful in solving some of the challenges in quantum chemistry. And so every quantum chemist pretty much focuses on finding ways how to approximate the Schrödinger equation to treat certain molecular types of molecular systems. And so this type of figure here is very well known to most quantum chemists, and it pretty much tries to reflect how different approximations to the Schrödinger equation fall in terms of their computational cost. These are calculations that need to be done on high-performance computing infrastructure, and what type of systems in terms of length and timescale, how many atoms can be treated and how many electrons. And so there's always this trade-off. If you want to be very accurate, the system sizes you can treat are very small, and if you want to be very fast, then this costs you in terms of accuracy. And machine learning can very much help to break this cycle, and it's been used very successfully in the context of that. Another more conceptual approach how machine learning can really change what we do in chemistry is to explore chemical compound space. And so chemical compound space is pretty much the space of all known molecules. And there are very many known molecules, but there are much, much more unknown molecules, molecules that are possible by looking at all possible permutations and combinations of atoms. And in fact, there are more atoms, possible molecules than atoms in the universe. And the problems we have in exploring chemical compound space are similar to exploring the universe, because we basically don't have the tools to look at each and every corner of this space. And we don't know how the space looks like and how many dimensions it has. So it's a very similar problem. So machine learning can really be a tool to help us understand how this space looks like and how we can try to identify molecules with very special properties that, pharmaceuticals, catalysts, and so on in this space. And so the challenge boils down to having a problem of, composition of atoms, certain atomic positions R, and atom types, so, Z, and they basically make up molecules, they make up materials. And so the energy that comes out of these quantum mechanical equations is a continuous function, and all properties are continuous function of these coordinates and positions. But we can always only for a given geometry and for a given R and Z get the output of this equation. And so the Hamiltonian that governs this encodes a lot of physics as well. It obviously, if I rotate this molecule rigidly, if I move it around, its energy doesn't change. It stays the same. If I label these atoms 1, 2, 3, 4, 5, 6, 7, and I swap those labels, nothing changes. This is something about the indistinguishability of atoms. And so a model that will try to parameterize these observables, these quantities, will need to capture all of these symmetries that are part of the Hamiltonian. There are lots of examples where machine learning has been used extremely successfully in chemistry, particularly supervised machine learning. So parameterization of quantum mechanical properties. And so quantum mechanics, quantum chemistry allows us to calculate energies, wave functions, right? And from those, we can calculate all sorts of properties, molecular polarizability, dipole moments, you name it. And so there's been a huge success in building continuous representations of these properties from and interatomic potentials from quantum mechanics. And that nobody, hopefully nobody is upset if their name doesn't show up. There's been loads and loads of successes, loads of great groups here. And I'm just giving a couple of examples of some of the works here. And so the basic idea is that we perform quantum chemistry calculations, we get wave functions, and we get our observables, and these observables can be parameterized with machine learning, right? So the machine learning models basically take the role of connecting the total energy, polarizability, these properties with these continuous variable spaces. And this has been done with kernel-rich regression, neural networks, deep learning, all sorts of different types of approaches. One example I want to give for how this can be done is an approach that underpins the model that we've been using, which is also developed by Christoph here. And this is called the Schnedt atomistic deep neural network model. And the idea is that we look at a molecule as a composition of atoms. So each and every atom has a descriptor, and the final output property we want to predict is a sum of all of these different atom features. So the total energy that is predicted here in this model is then a sum of all of the different atom features that are created in this deep neural network sequence here. And so the input variables are the atom types and the atom positions in space, in Cartesian X, Y, Z atom positions. And the purpose of this network is very much to replace the discrete space of these different positions with a continuous space that connects the output property we want to predict with the atomic positions, with a continuous filter. And the way how this works is that the atom types are embedded with random initializations, and they are convoluted with continuous filter functions which encode these distances between atoms. And so there's also a radius, a cap in terms of distance we can put on this. But in principle, these interaction layers encode how different atoms interact with each other and how those interactions then define the features of this atom. So each and every atom is convoluted with the actions with all of its neighboring atoms. And so we do this in several passes through these interaction layers and with a prediction output. And then we basically train by back propagating through this model. And this can be done for any sort of property. Now, the idea of the paper that I'm talking about now is not necessarily to do this sequential runoff. We've got some properties, and then we, machine learn, train models on these properties. But we had the idea of going a bit further than that to say, well, yes, we can. It's been shown that we can use machine learning to train on quantum mechanical data, but can we go a bit deeper into the equations and maybe try to train the wave function itself? Because clearly the slow part, the bottleneck, is this bit here, right? So if we have a machine learning model of the wave function, the evaluation of properties is something that we know how to do, because there's this huge engine, many different software packages that do this for us. But if we have a machine learning model of the wave function, we can then predict these as well. And we can think about ways how to connect this back into quantum mechanics to solve different problems. And so this was the motivation of this work. And so the goal is to develop a machine learning model of the Hamiltonian, of the molecular wave functions themselves. And so this is the part where I have to talk a little bit about the way how quantum chemistry works. So the way how we typically do quantum chemistry is, we solve this equation or an approximate version of this equation, and we need to represent the molecular wave function in a basis. And the basis how we typically represent it are atomic orbitals. So the orbitals you saw in the video, which are these, nice little spherical harmonic lobes with some radial functions. And so every wave function we build as a linear combination in this space of atomic orbitals, and that transforms our equations into generalized matrix eigenvalue equations. So now the Hamiltonian is an actual thing, right? It's a matrix that is represented in the space of these atomic orbitals. And they have, they're non-overlapping, so we also need to have an overlap matrix. And so these quantities here, they actually can be calculated quite straightforwardly. And every quantum chemistry software package can do that. So our plan was to take these representations of Hamiltonians as we can create them and use them as training data in our model. And so we're calculating for each and every molecule here that's shown, for example, malonyl dialdehyde, we would calculate about 25,000 data points, 25,000 instances of this Hamiltonian corresponding to different atomic positions. And we use this as training data for the model, right? And so now I'm going to get to the model, and that hopefully will explain a little bit better how we do that. So this Schnorr model, as it's called, which is Schnet for orbitals, is the idea of this is very much similar to this original Schnet atomic layer. But instead of describing the problem, the Hamiltonian, the molecular wave functions, as just being convolutions into all the different atoms, we're looking at atom pairs now. So the model itself, again, takes the atomic positions that define the molecule, and we're the atomic types. So we, again, have initial random embeddings for these. We take the distances, all possible distances between the atoms, and those go into the Schnet layer. And this is very much the same as you saw before. So we have a continuous filter that embeds the distances, and we have a convolution step that adapts the atomic features to account for these distances. So we very much train the environment of the atom into the essence of the atom. But then there's this additional step now, which is this Schnorr layer, where we now connect pairs. And the way how it works is we take the atomic features that are created in the model, and they go into a factorized tensor layer, which connects distances and these atomic features into pairs of pairwise features. So these Hij you see here, those are pairwise features that connect each and every possible pair of atomic orbitals, right? So if you look at this matrix here, which is for an H2O water molecule, we see all the different basis functions that define the atomic electronic states in this model. And so there are some that are just in oxygen, some that connect oxygen and hydrogen. And so we're trying to capture all of these different elements here. And these pairwise features, after they are convoluted with the distances, they are then used in simple two-layer neural networks or multi-layer perceptrons to describe the pairwise interactions within the pair of these orbitals, but also, crucially, how this pair of atoms is affected by its environment, so by all of the other atoms in the molecule. And so all of these things go together to define pairwise features, which we then use here to predict these off-diagonal matrix elements and these diagonal matrix elements. So elements between atoms and within the atom, between different orbitals. And if you were to ask me what is the most crucial aspect of this layout, which obviously is quite complicated, it's this bit here. And so this is actually where we don't just use the distances between atoms, but you can see here we're using the directional distance vector. And this is quite crucial. It took us about 2 years to figure out how important this is. Because if you think about two little dumbbell lobes, one with plus and minuses, and if we rotate them against each other, then it's quite important how the plus is aligned to the minus and vice versa. And to encode this information into a deep neural network, you must have some directional information. And so this is exactly what this does. So these pairwise features that are passed through several layers of these Schnorr layers, depending on how much angular momentum, how high angular momentum is in your basis set, those are then multiplied with these directional distance vectors and allow us to predict on-site and off-site blocks of the Hamiltonian.
Also, by the way, we can also use the atomic features that come out of here. They are summed up again and passed through the Schnorr layer. So we can use those again to also look at scalar properties, energies, and all the other properties that other networks have been able to predict in the past. And so one of the crucial aspects of predicting molecular wave function is capturing their rotational dependence, which is a lot more complicated than just looking at rigid rotation of molecules and how the energy is affected. Because molecular orbitals aren't nominally invariant to rotations. You know, they have to rotate with the molecule, so they're more equivariant with respect to rotations. And you can see here these little red and blue blobs that you see. These are molecular orbitals for H2 that the model has predicted successfully. And you can see how they rotate with the molecule as we rigidly rotate it around. And we achieve this. So the model has the flexibility to capture this rotational equivariance. And we achieve this by data augmentation. So we basically, for each and every data point we have, we rotate the training data to sample some of the rotations and then brute force learn them into the model.
Yeah, can you explain a little bit about RIJ? Is it a directional stance, and how this stance is directional?
IJ here refer to two atomic orbitals, right? Inside. And so basically what we're looking at here are, in this case here, we're only looking at the absolute distance between atoms. And what the Schneid layer does, it basically makes a continuous representation of all the possible distance in your system and generates a filter, a radial filter based on that. And that describes the environment of your atom. So what we're doing here is we actually need to know in which direction the atom is connected to the other atom. So there's an actual sign associated with that. And that sign is quite crucial to give the deep neural network the flexibility to capture the different plus and minus combinations of orbitals as they interact.
Interesting. Oh, makes sense.
Right?
Thanks.
So and we try to do it without that. The minute you take this out, it all falls to pieces. So it makes sense if you think about semi-empirical method. Sorry for the non-quantum chemist. This is getting a bit off track. But in semi-empirical methods where tight binding approximations, you would typically have interaction integrals that you can, pairwise interactions, you can represent without any directional distance vectors. But if you want to represent them in Cartesian space, you must have these distances to rotate them against each other. And this is pretty much in line with what's going on there. And so we know we can get the rotational dependence of these orbitals right, which is really one of the most crucial aspects here. And again, permutation invariance is also satisfied intrinsically by the way how these embeddings work. And so when we look at the model performance, it's actually quite nice. So for the ethanol molecule, we can see that. So what you see here is the mean absolute error on the test set for the energy levels, so the molecular orbital energies. And these are the corresponding molecular wave functions. And so HOMO here means highest occupied molecular orbital, LUMO lowest unoccupied. So these would be the ones populated with electrons. These would be the ones not populated by electrons. And we can see that we're doing slightly better for the ones that should be populated. And you can also see this dividing line here, where the error suddenly jumps up, is between the occupied and the unoccupied states. And there's a couple of ways how to understand why we're doing so much better for these occupied states, where you pretty much see no difference in the prediction and in the reference in the training data. And it's because they are very much, they define the equations in these density function theory equations that we use to generate the training data, while these unoccupied orbitals are not strictly bound by these equations. And they're also dominated by higher angular momentum. So to get these right, we would need to have more passes through these Schnorr layers to really get all of these interactions in. So overall, we're quite happy with how this does for small molecules like this. And because we're training on molecular dynamics data, on dynamics that are performed on these molecules, we can now use the model to also perform ab initio molecular dynamics from the Schnorr model, and then see how the orbitals are affected by this. And so this is basically what this video here shows. On the left, you can see a molecular orbital of the malon dialdehyde molecule predicted by Schnorr and the corresponding training data reference. And it's very hard to see a lot of differences here. You need to really look closely in certain cases to see how some changes are shown. what's interesting here, let me rerun this quickly because I think it's quite nice. What we're looking at here is the hydrogen being passed from one oxygen. The red sphere is an oxygen, hydrogen being passed from one oxygen to the other. And the model really captures how the wave function follows. And that was quite a good sign for us to see that we've got something here that works. So the question obviously now is, what can you do with this thing, right? What's the point? And so there's a couple of different applications that we can foresee in the future for a model like this. And one is very much with this idea of, if we have a machine learning model of this, can we feed these back into quantum chemistry? And the other one goes into solving inverse problems. So what type of inverse molecular design can we do? And I'm going to talk about both of these ideas of applications now. And if you want me to go back to some of the model, feel free to just interrupt me. So the first application is one where we thought, so how can we think about closing this loop? So this idea of unifying machine learning and quantum mechanics, where we have quantum mechanical data, we can construct the wave function, but can we somehow feed this back into quantum mechanics? And we can, for example, use the wave function itself as a starting point for quantum chemistry calculations. So in some of the calculations we do, we need to have, these are integral differential equations. They need to be solved self-consistently. So they need a good guess to start off with. So we can use this, and we can see that the number of steps we have to take in order to solve the problem can be dramatically reduced. And so this is an interesting aspect. We also have tried to take these wave functions to put into higher level calculations, where we, for example, where we use quantum chemistry to study many-body interactions. So to look at correlation energies between molecules. And so, for example, we can take these predicted wave functions and feed them into coupled cluster calculations or MP2 calculations. So these are perturbative calculations that give us a better prediction of the correlation energy between electrons. And obviously, this is just a proof of principle of the different things that are possible. The way how you need to think about the problem, and I think this is universal for physics in general, is that there are always numerical bottlenecks to complex simulations, right? And by the way, if you want to know about a good motivation why you need machine learning to simulate simulators, a few weeks ago here on this channel, Tobias Pfaff from DeepMind gave a talk on graph neural networks, and he gave a really nice introduction why anybody would care about simulating simulators with machine learning. And a lot of the points he made are also applicable to quantum chemistry. And so there are these numerical bottlenecks, and I think machine learning is a good way how to address them, particularly if we have integrals, which we keep solving over and over again. And so I think the future will hold a lot of interfacing between physics-led problem solving, physics-led simulations, and machine learning. And in tandem, I think you can achieve a lot there. But something that's a bit closer to my heart as a chemist is, of course, what can we learn about the chemistry of systems now that we have a model for the wave functions? So, for example, once we have the wave function, we can analyze the chemistry of a molecule. So for this malon dialdehyde molecule, these carbons and oxygens here, we can calculate what is the net charge, how much charge did this atom pick up due to its interaction. So this carbon is slightly positively charged. This oxygen is slightly negatively charged, right? We can also calculate the strength of bonding between atoms. So this is the equivalent of two bonds, a double bond between this carbon and oxygen. This is the equivalent of close to a single bond for those two. And so with this machine learning model, we can study the dynamics, like, again, this hydrogen proton transfer from left to right. And we can see how the model predicts how the hydrogen, the charge on the oxygen changes from close to neutral to slightly negative, because the hydrogen moves from one oxygen to the other, but it leaves its electron behind. So it moves as a proton, as a positively charged nucleus. And we can also look at the bond order, and the model nicely predicts how the hydrogen-oxygen bond is broken as the hydrogen moves from left to right from this oxygen, and how the new bond is formed with the second oxygen. And you can see basically that the prediction and the reference, the training data, test data, they trace each other. So there's a lot of different ways how you can apply this moving forward. The other aspect is, of course, this idea of how can we better explore chemical compound space. And one of the key features of this model is that we provide an analytical parameterization of the wave function. So that the model at the end, it has a lot of internal parameters and it has a high variability, but the end result is an analytical function for the wave function, which means we have we can differentiate it. And so by differentiating it, we can basically solve problems of observables that depend on the wave function itself in terms of its dependence on the input variables. And so there's this concept of inverse chemical design, which is quite important in a way that, chemists are very good at taking structures and then characterizing them. And quantum chemistry also, you take a structure, you have certain R's, and then you predict what you get. But the inverse problem is so much more important because the questions we ask in real life are, I've got a cold, I need a molecule that does this and that to fix it. Or I've got a coronavirus and I need a molecule to help me, quite relevant these days. So the problem is an inverse problem where we have a certain molecular property, a certain electronic property that molecules need to satisfy, and we want to be able to identify which structures have these properties. And so by having an analytical representation of the wave function and its dependent properties, we can now do gradient descent on this. And in this simple example here, you can see how we can say the energy gap between the highest occupied and lowest unoccupied state, we can basically tune this gap by asking how does the structure have to change to give us the highest possible gap? And then we see that we need to stretch the bond on the oxygen that doesn't have a hydrogen. But if we want to have the lowest possible gap, we need to contract the bond. We need to stretch the bond with the oxygen that actually has a hydrogen. So it gives a bit of a glimpse into what's possible when doing when solving these problems. There's lots of remaining challenges, and as we go to larger molecules, we see that we need to find better ways how to deal with accuracy. So we just have a new preprint up, and I'm not gonna go into too much detail because I think otherwise I go over time. But as we go from molecules that are larger than this malondiene aldehyde and others, we get to Hamiltonian representations that are very large, right? So, for example, this molecule here, everybody's very familiar with. It's our good friend aspirin. And the representation here is 222 by 222 matrix sizes, and you can see that the prediction errors that our model gives are much, much, much higher. And they basically also go into this occupied space. And so the resulting orbitals are really far away from the reference. And the reason for that is simply that the sheer dimensionality of the problem is hard to cope with. So we're working on finding better ways how to pre-process the training data. And the quantum chemistry is quite helpful because we can do arbitrary basis set transformation, right? It is a pure choice to use atomic orbitals. We can use any other basis. And so, go ahead, Mehrshad.
Can you explain a little bit the inverse design process? As in terms of search space and how you tackle this?
So the way how we present this here in the paper is quite trivial in a way that once you have a gradient on the wave function or on any properties that depend on the wave function, we can just follow that gradient and see where it takes us. But obviously there are much, much more sophisticated ways how to perform inverse design. And so that would involve, for example, a global optimization in this variable space. And the variable space must be one that looks at lots of different types of molecules, lots of different configurations, compositions, and that explores these efficiently. And at the moment, we don't have this, but this is something we envision to do in the future with this problem, and that lots of people have explored for other molecular properties before.
Makes sense. Thanks.
And so the only thing I want to say here on this problem is that we can change the basis set in which we represent our Hamiltonian, right? We can, instead of using atomic orbitals, we can use any type of effective basis that we think is most suitable, and that limits the dimensionality of our Hamiltonian. So by going from this atomic orbital basis to this effective optimized Quambo basis, I'm not going to go into much detail here, we can reduce the dimensionality of the Hamiltonian for aspirin from 222 to 90. And so suddenly we get a much more consistent prediction error for our energy levels here and for our wave functions. And this is something that now allows us to go to much larger molecules and hopefully also hopefully also move forward in terms of going into more complicated materials, right? And so just to wrap up on this, where the Schnorr model is very much a proof of principle that we can predict molecular wave functions and their derived properties, and we can in an atomic orbital representation. The key here is really that we're using a representation that is common in quantum chemistry, and in doing so, we can now interface with all the existing software packages that are there. Right? There's so many powerful packages that have been developed over the years, and we can interface with those by using the representation that they understand. Now, we're dealing with this rotational equivalence by data augmentation, which is a plus and a minus. It's a plus because the model is flexible enough to cope with it, but as you go larger, you're running into basic dimensionality limitations. So for very, very large systems, you're running into this situation where it might be more sensible to restrict the flexibility of the deep learning model and hard code more of the physics into it, right? To encode some of the symmetries more explicitly. And the model we currently have is one model per molecule for all the possible configurations of a molecule. But we're thinking about getting a model, we're working now on a model that would allow us to predict lots of different compositions, so different number of atoms, different types of atoms in one go. And we want to go towards materials as well and think about better how to integrate this model into inverse design in terms of generative models, for example.
Oh, thank you. Thanks a lot. It was very impressive. I really enjoyed it. I was wondering why, from the beginning, didn't you directly train on wave functions and eigenvalues instead of Hamiltonian?
That's a brilliant question, and we did do that. We failed miserably. It cannot be done. I say it cannot be done. Everything can be done if the right people do it. But so there's a reason why. Okay, let me go back just to explain, because Mehrshad is an expert. He knows what I'm talking about here. So the question is, why do we train on these Hamiltonians and overlap matrices in this basis representation rather than go right for the target, which are these energies and wave functions? And the reason is the generalized eigenvalue problem. Because if you look at how these Hamiltonians and their matrix elements change as a function of coordinates and change as a function of atom types, they are very, very well behaved. They behave in very smooth ways. If you look at how these molecular orbital energy levels behave as you rip atoms apart and as you change the molecules, they change in very odd ways. There are discontinuities in their behavior, and there are degeneracies. They're very hard to predict. And because you basically have your machine learning model now has to do all the hard work of the eigenvalue problem, right? So what we were trying to do is we were going to go in before the eigenvalue problem hits us, predict the Hamiltonian in whatever representation you want, really. I mean, that's all up to you. And then you just put it into LAPACK, right? Because there's much smarter people that have solved that problem. And there's even one more crucial aspect here, is that the phase, so the signs of these wave functions, of these coefficients, they are not unique, right? If you solve this eigenvalue problem twice with very little differences, you can get pluses where there's minuses. So you have this whole phase problem that you have to deal with.
Interesting. Yeah. Thank you. And was wondering, what do you think would be the future of using ML in computational chemistry, quantum chemistry, and what are the potential research areas?
So my thinking on this has changed a bit over the last few years. I think it's going to be completely transformative. It sounds silly, I know, but I think we're going to be at a point in 5 to 10 years where we're not even going to talk about machine learning and quantum chemistry, because it's going to be incorporated, embedded into every single thing we do. And that goes into the actual numerical technical bits of the developers. As I mentioned, all the numerical bottlenecks. Why the heck do we keep evaluating the same integrals over and over again if a machine learning model can just predict them for us on the basis of all the calculations we've done in the past? And in the same case, so there's clearly big changes in the technical software aspects in how we do things. On the other hand, I also hope that we're really changing the way how we as chemists think and work, and based on this idea of chemical compound space and how to explore it, right? How to go away from this idea, structure gives us everything, rather than I've got these properties in mind, and what are the differences, the changes, how do I need to tailor and design molecules? Thinking more like an architect than a chemist, if you will. And I think that machine learning models that focus on inverse design can really help with this.
Okay, that makes sense. And finally, I wanted to ask, like, I don't know. Let's see if I have any other question from audience. And yeah, not yet. So, in terms of using machine learning, what is the procedure for gathering data? Like someone asked, like, do you use like, what is the procedure you use? Is there any data set? Is there any, like, it is in a general picture, like, what is your proposed way of yeah, providing enough data? Because neural nets require lots of data. So what is the way you're solving this problem?
So this is, by the way, this is the aspect why I think that a lot of computer scientists and machine learning experts should jump onto chemistry and onto physics, because it's one of those, machine learning models are developed to work with a lot of data, right, as you say. But chemistry, quantum chemistry, physics doesn't have a lot of data. Every single data point is extremely expensive. It's a huge high-performance computing machine sitting somewhere, burning energy of insane amounts. So every single data point is precious here. And this is basically also a technical challenge for the machine learning experts. How can we design models that build on the right physics, that are physics-led, that are less naive, that can work with scarce data? And then the chemists have to come in and think about the other huge challenge, which is how do we create meaningful training data, right? How do we sample complex chemical spaces? And I don't think there are good answers to this yet. There are lots of problems with creating training data sets in chemistry. So for this particular problem, the way how we did it is that we use ab initio molecular dynamics. So we run dynamics where we follow the classical equations of motions of atoms based on the energy landscape that comes out of the quantum chemistry. And so that samples lots of different configurations, and then we take a subset of these configurations, about 25 to 50,000 data points there. And so for each and every data point, we feed the Hamiltonian in this matrix representation to the model. However, I should also say that the cost function, the loss functions we use are, they don't just train on the Hamiltonian, we also train on different properties. So you also partially train on the eigenvalues. And there's a bit of a balance in what you can achieve by mixing weights.
Interesting. Also, I know that computational chemistry or computational methods for chemistry purposes usually have a high computational cost. So, any idea how roughly, like, how heavy it would be in terms of computational cost?
So, sorry,
Like
do you mean the evaluation of the neural network?
Yeah.
So the cost of evaluating one of these Hamiltonians here is obviously more computationally costly than a classical interatomic, like a classical force field, because it's just harmonic springs and stuff, right? You can do that on paper if you really want to push it. So rather than the microseconds that are typically achieved in evaluating these force fields, we're talking about milliseconds here, right? But all of this is GPU enabled in the software infrastructure we have, so you can really benefit from that as well. And of course, I should mention, if you're interested in energy levels, then you still have to pass the Hamiltonian through an eigenvalue solver, right?
Yes.
So the intrinsic limitation is basically the scaling of the eigenvalue solver. But there's amazing eigenvalue solvers out there.
Exactly. Awesome. Thanks a lot. So seems that there's no more question from audience, and yeah, I really want to thank you for taking your time and for your great presentation. I personally really enjoyed it, and based on the comments I got from audience, they really liked it. And
Sorry for the audio mess up.
and yeah, and thanks everyone for joining us today. And looking forward to the next talk in this stream.